Good morning, everybody. How are we doing? Pretty good, pretty good. What tests are coming up for you guys? We don't have a test for a little while in here,
I
so
already had a test.
had tests, chem tests, math tests are kind of done for the moment. Yeah. They come in waves, right? It's like you're convinced the teachers schedule them all on the same day all the time. And we do. Before the start of the semester, we line up all the exams and we say, how do we put maximum pressure on the human mind? No, we don't do that. All right. I demonstrated polarization last time. And I want to just get a little bit more into it because it is incredible, right? Let's try to understand what's going on here. So this is a weird diagram. I get it, right? But this is what an electromagnetic wave looks like. This is what light looks like if we interpret it in the context of a wave in the electric and magnetic fields. Now, this is supposed to be a 3D image, right? It starts with the yellow, goes up and then down and then up and then down, right? And then at 90 degrees to it, sort of coming out and then into the screen, right? Is supposed to be this magnetic field. So this is how we model light when it comes to these Maxwell's equations, the electromagnetic wave that Maxwell discovered. Now, as the field wiggles, the direction of propagation is perpendicular to both the electric and magnetic field. So yes, there's some right-hand rules and things that go in there, but don't worry, we're not going to do them. That's more advanced stuff. But when you think of like a light beam or a light ray or a wave of light coming at you, okay, it's going to be wiggling with electric field, and it's going to be wiggling with magnetic field, right, doing this as it comes at you, right? So it can, of course, we can tilt that, right? We can tilt the electric, but the magnetic field will always be at 90 degrees, and unpolarized light can be any rotation that we like. But when we polarize light, right? So like if we just looked at the electric field, okay? And so we're just looking at sort of the wiggle up and down, this wiggle, this like electric field, this unpolarized light, the electric field can be wiggling anyway, and this is probably coming at us out of the screen. When you polarize the light, you get rid of all the wiggles except for one direction. Whatever the rotation of the polarizer is, right? So if you set your polarizing axis at 45 degrees, then your light will only be wiggling this direction, okay? It's a lot like a fence, right? Like mechanically, if you were playing with a rope and you were sending waves down a rope, if you send it through a fence with a vertical slats in it, right, then you can wiggle that rope directly through that fence opening, right? There's nothing going to get in the way. But if you turn the fence, right, against the direction of the wiggle of the rope, or in this case, maybe you have a polarizer, and I did this last time where the polarizer was vertical and the next polarizer is horizontal, then the rope can't wiggle, right? It's only going up and down, and now you're forcing it to try to go sideways, and there's no sideways part. Light does the same thing. Polarizers act like a fence, right? And they force the light to only wiggle in one direction, okay? So the way that we can like calculate with this, let me make sure I remember what, yeah, there it is, okay? So it's called the law of Malus, and that was some dude's last name, okay? But basically we can determine how much light is going to pass through two polarizers if we know the angle between the polarizers. Note, it doesn't really matter sort of what the first angle is as long as we know the relative angle between the two polarizers. So the first polarizer could start at like 90 degrees straight up and down, and the next one could be horizontal at 0 degrees. What matters is that these are 90 degrees with respect to each other, right? The first one starts at 45 and the next one's at 0, right? Then the angle between them is 45 degrees. Okay, so it doesn't really matter how their global rotation. What matters is the angle between them. So concentrate on that. To calculate the intensity, your book uses the symbol S, which is weird. Most physicists just use I for this. but we'll go with your book, okay? The intensity of light, okay, that's coming out and what the observer is going to see will be equal to the intensity that struck it in the first place times cosine squared of the angle between the polarizers, okay? So in this diagram, they have an E naught. So we're just going to say S, right? And that bar over the top of the symbol just means average. We're being pedantic there, right? But the first polarizer, so if you have an intensity, I don't know, of 100, okay, coming in, 100 watts per square meter. Intensity is always energy per area. Then the first polarizer is automatically going to do what? Do you remember what I said yesterday? The first polarizer always knocks the brightness or intensity down by half, right? So in between, we're going to have 50, right? The equation in the box will tell you what you're going to have on the other side of the second polarizer, right? So problems, physics textbook, physicists, they'll try to trick you, okay? They'll try to trick you in the sense of they'll tell you the intensity that goes into the first polarizer, right? But the law of malice, it calculates what the intensity is going to be on the downstream side of the second polarizer. And what you need to put in for S naught, okay, is, in this case, would be the 50. It's what hits the second polarizer after the light has already gone through the first polarizer. Now, cosine squared of theta, what happens if the angle's 90? What's the cosine of 90? It's 0, right? So you get 0 intensity when you have polarizers at right angles to each other. So I already did the demo with the polarizers. Where did I put my... Do I look cool? What are these? These are 3D glasses, right? Okay. Used in movies and all that kind of stuff. They're a little bit better nowadays. These are a very old pair. Okay. We can tell that they have polarizers in the lenses, okay, because we can cross two of the lenses against each other, right? I don't know if you can tell, but that's like just black right there. Okay. So these are definitely polarized lenses. But why do you need 3D glasses to see a 3D movie? I mean, like, movies are normally what? 2 dimensions, right? They're broadcast on a flat surface, right? And the illusion of the third dimension is pulled off by perspective. In a 3D movie, and it's not very popular anymore, is it? Yeah, I mean, like, the only reason to do 3D is, like, if you're watching Avatar or something, right? But, like, to get 3 dimensions, for our brain to interpret a 3-dimensional image, what we have to see are 2 images that are very slightly offset from each other. And you can see the offset in your brain, okay? If you like, you can do this experiment right now. Just hold your finger out at arm's length, okay? And then, like, if you can focus on your finger if you want, but it kind of, you can look at your finger or you can look far away, it doesn't matter, right? But hold your finger out in front of you at arm's length, and then open your right eye, and without moving your eye or your finger, switch to your left. What does your finger do? It jumps, doesn't it? Why does it jump? One eye, right, depending on where you're holding your finger, right, will look at their finger straight, right, but the other eye is looking at it slightly off at an angle, right? And so our brain stitches together the 2 pictures and tries to give us depth information about that. It's not the only way we perceive depth. People with one eye or vision loss in an eye, they can still get depth no problem, right? But the 2 images really is kind of the main way our brain does that. So to get a 3D movie to happen, to see stuff on the screen, pop out of the screen kind of thing, right? What we need to do is we need to give you 2 images. They need to project 2 images on the movie screen, but then we need one eye to only get one of the images and the other eye to get the other image. Have you ever, anybody ever been to a 3D movie and you take your glasses off? Do you see, what do you see? It's kind of like fuzzy, isn't it? Okay. And also, if you ever do it again, notice it's really bright. Like they turn the brightness way up. Why do they have to turn the brightness way up? Because you're cutting half of the intensity, right? Right off the bat. So what happens is in these glasses, I don't know which one is which, but we'll say this side is vertically polarized and this side is horizontally polarized. So one of the images on the screen has vertical polarization and the offset image that's displayed on the same screen is horizontally polarized. So that means the horizontal picture can only get into the horizontal eye. The vertical can only get into the vertical eye. And your brain sees two images and tries to put together those two images into three-dimensional space. I'm one of the third of the population that just gets a raging headache whenever I am forced to watch a 3D movie. It's usually because the way they shoot the movie, they have to shoot with a camera that has two different lenses that are offset from each other, and typically they don't shoot with a normal IPD or interpupillary distance, the distance between the centers of your eyes. What they'll do is they'll shoot with a camera that's got like an exaggerated distance between the two eyeball camera, that they're shooting with, and my brain can't handle it. Like my brain understands that there's something wrong here, and I just fight the whole sensation the entire time. So what usually I do if I'm forced to watch a 3D movie with friends or something, okay, I will grab two pairs of glasses. I will punch the lens, right, I'll take and I'll make a pair of glasses. I'll just swap the lenses around so that my glasses are either both vertical or both horizontal polarizers in there. And so that way, when I put them on, I'm only seeing one image. I don't see any 3D, right? But I just see the one image, and I'm good to go, right? So that's my trick. That's my hack for not getting a headache. I watched Avatar in the theater. I wore the 3D glasses the whole time. They didn't give me two pairs. And so I got a raging headache 10 minutes into the movie. To this day, I can't watch blue people on the screen without getting a headache. Like I sat down to watch Way of Water, okay? In 5 minutes in, had a headache. It was on a flat screen in my living room. There was no 3D going on. But I still got the headache because my body remembers. Oh, blue tall people? Headache. So, yeah. All right. Polarization can happen for a lot of different reasons. Where you'll run into it on a daily basis is in the sky and also reflections off of very shiny surfaces. So things like metal and glass. At a certain angle called Brewster's angle, the reflected beam coming off of a surface can become horizontally polarized. We as human beings, when we perceive horizontal polarization, we see it as a very bright, glare. It's a really just intense reflection that's coming off of the surface. And it's not so much that suddenly the sun got brighter at that point, right? Okay? It's just that as the light bounces off, say, the hood of a car, right? Or its back window or something like that. The light bounces off. It might bounce at Brewster's angle, and at that angle, the light coming in that was polarized whichever direction, or unpolarized, bounces and starts coming at you horizontally. And our eyeballs have evolved to be sensitive to that horizontal polarization. So when you purchase polarized sunglasses, what are you buying? To cut the glare, which way do the sunglasses have to be polarized? If horizontal is going to look really bright and glary, what do you want to do in the sunglasses? Vertical or horizontal? Vertical, right? They'll put vertical polarizers in to cut that glare as it comes through. This is a very terrible picture. I know this, and I judge it to be so because I took it, okay? And it's not terrible because I took it. It's terrible for a lot of other reasons like composition and and the light, the glare coming off of the surface. It's hard to kind of tell what it is because we got a lot of light in this room. But this is a piece of driftwood. This was a stump on the beach, okay, that had been covered in water, right? And if you're looking at this picture and you're going, I really can't make out what's going on, that's okay, you're not supposed to. Do you see all of the glare? Do you see all of the highlights? Do you see all of the really bright reflection that's coming off of the subject, the piece of wood? Okay. This is a picture that was taken with a camera that did not have a polarizing lens on the front of it. Our cell phone cameras, our pocket cameras, they can't do this. Okay. They sort of try to cheat it in software a little bit. But an actual like camera with good lenses on it, you can put a polarizing filter on the front. As a matter of fact, I think I have one. Yeah. This is my broken one. This is what you get, cracks right through the center of your polarizers when you drop your polarizer, okay? But what happens is this screws onto the front of a camera lens and then it rotates. Okay, so I can actually rotate the plane of polarization of light as it comes through the camera lens. If I do that and I get the adjustment correct, do you see how the picture changed? Right? All of a sudden, it's more pleasant, isn't it? The colors are warmer. You're able to see the definition of the wood better, right? Some of the intensity of the reflection goes away, right? In photography, being able to mess with the polarization axis of the light as it comes through your camera is pretty important. And like I said, our cell phones kind of try to cheat this a little bit. They'll realize that there's parts of the picture overdriven and they'll use, it's not really AI, but they'll use machine learning to try to correct some of that as it comes in. But again, right, very blown out, not a good picture at all, right? This one is at least a little bit more pleasant, okay? Here's another example of what happens in the air, okay? So air molecules, if they're hit a certain direction, can re-emit light with polarization. If you're wearing polarized sunglasses, you walk outside, you might notice looking one direction, the sky looks blue, and looking a different direction, it looks black, okay? You're seeing the direction of polarization of light as it comes through the atmosphere. But do you see the difference here between these two pictures? Look at the top picture. Look at the sky. I did not take these pictures. These are awful pictures, but they are representative of the effect that I'm trying to tell you about. Do you see the sky up there? Do you see how it's like blown out white and you really can't see any detail? Very nearly the same perspective, but they just put a polarizing filter on the front of the lens. Do you see the sky? Do you see what happened? So polarizers can cut like haze and intense reflection that's going on in the atmosphere in the case of a picture. I want to be here. I just kind of want to be here. What's one of the things that makes this picture amazing? There are no people in it. Right? But this, note the sort of, we can see kind of some of the clouds, right? But look at the ocean here, right? Can you see anything below the water, really? I mean, it looks like there's some rocks or something out here. This is the picture without the polarizer. Here's the picture with. Do you see the difference? I mean, the sky changed. We can see more clouds. But look at what happened to the reflections on the water. Do you see how now we can almost see into the water? Okay, and some of that horizontal glare gets removed. So being able to do this either with your Mark I eyeballs wearing polarized sunglasses, or being able to capture it in a video camera or a regular camera, right? Having the ability to do this polarization trick can really lead to better outcomes in the photography and visibility, all that kind of stuff. If you have sunglasses and you look at the back window of a car, you might have noticed that there's like a checkerboard pattern that shows up sometimes. That pattern is being caused by the layers of safety film that are in that glass. It's causing polarization artifacts in the glass. Take your glasses off, the glass looks like glass. Put the glasses on, and all of a sudden it looks like a kind of a checkerboard pattern of dark and light. Airplane pilots cannot wear polarized lenses in an airplane, because if they do, they have run a chance of not being able to see out of the airplane's glare shield, the windshield, the glass in the front of the cockpit. Again, because glass and other things can rotate the plane of polarization and cause problems. This is a complicated drawing of what happens on a computer screen to make computer screens have changes in intensity. Not all liquid crystal displays work this way. All liquid crystal displays work this way, but not all flat panels are LCDs. Okay? Some of them are OLED panels, which is a different technology altogether, organic light emitting diode. But a liquid crystal display has to use a polarizing filter in it in order to be able to control whether or not a pixel is seen or not seen, or has a certain intensity. The liquid crystal in these displays, if you apply a voltage across them, can force a direction of polarization. The liquid crystal with that voltage across will orient itself and cause a polarization to happen. If you have a polarizer built into the display, then you can turn that pixel on and off effectively, right? And depending on the amount of voltage, you can change the rotation, and Malice's law kicks in, and you can have various intensities. I've got the computer up here at the front of the room, right? And I know that this is an LCD or liquid crystal display because if I take my polarizer and I hold it up in front and I rotate it, what happens? It goes dark, doesn't it? Okay. As a matter of fact, the axis of polarization of this display, I can tell you right now, is at 90 degrees to whatever my polarizer is doing, right? I don't know if my polarizer is vertical or horizontal, okay? But you can see here that I managed to cut it out, right? And if I rotate it, it comes back. This is why people have trouble sometimes seeing their laptop screens when they're wearing sunglasses outside. It's not that your laptop screen can't get bright enough, maybe it is, but more than likely if you've got your sunglasses on and they're polarized and your axis of polarization, usually a manufacturer will try, I can tell this is a bad design, okay? Will try to have the angle of polarization be at some off angle, not horizontal, not vertical, so that when you're looking at it with sunglasses, it'll work. But if you're looking at a display outside and you can't really see it and you're wearing polarized sunglasses, tilt your head and all of a sudden it'll get brighter, okay? And you'll look weird, but it works. All right. So that's polarization, right? And a lot of the applications, right, that polarizers can lead us to. We're going to come back to polarization later when we get into quantum mechanics, because there's actually there's a mystery about polarization, but we will talk about that later. All right. I'm going to try to do all of chapter 25 with the time that's remaining. It shouldn't be that hard to do that because this is kind of a warm-up chapter to the main show, which is going to be lenses. What we're going to do right now is we're going to investigate mirrors, the principle of reflection. It was one of the 4 R's, or it's one of the 4 wave phenomenon that I talked about. 2 of them, reflection and refraction, right, can be done by either particles or waves, right? But what we're going to do for reflection is and the rest of our optics, by the way. So for the next, 4 chapters, okay? We are going to assume a model about light that is, number 1, a wave, that those waves emit from a source, right? Okay? The source vibrates, generates light waves, okay? And that those light waves spread out into 3-dimensional space like with spherical sort of wave fronts. If this looks a little bit familiar to you, you did this back in 2A with sound waves, right? Sound waves sort of spread out in all directions. But in optics, it gets a little bit cumbersome to be talking about these nested spheres of wave fronts or energy coming out of a source. And so what we do instead is we adopt this thing called the ray model. Okay? These aren't vectors, they're rays. They're lines with arrows attached to them that indicate the direction of propagation of the light. In this case, because our source is just a monochromatic source sitting in the middle, the rays would go out in all directions outward to represent, right, the direction of propagation of all of these light waves coming off of this object. But quite often what we'll do is we won't worry about the three-dimensional nature of this unless you're doing more advanced stuff. And instead we'll we'll simplify it, okay, into what we call principal rays, or in other words, the rays that really matter for figuring out what's going on. So case in point, okay, reflection. Now, they've attempted their darndest to make this look 3D, okay, but you really don't have to do that, okay. This, I would draw this, right? And first of all, I wouldn't lay a mirror flat on the ground either, right? I would draw a mirror like edge on, like I'm looking at my mirror. So here's a mirror, right? Okay. But you're looking at the edge of it, right? Okay. And we're going to let light come in one direction, okay? And on the shiny side of the mirror, right? And notice, and this is very important, there is this like dotted line that is normal or perpendicular to the surface of the mirror. In optics, everything is measured from this perpendicular line. Homework, physics teachers, cruel people will try to trick you. They'll give you like, oh, the light comes in at an angle from the surface of the mirror of 30 degrees. That is not the angle you want to use. What angle you're going to use instead? 60, right? Because it's the angle with respect to the normal that all of optics is based on, all the math, everything, okay? So the law of reflection says whatever my incident angle is, whatever angle I have coming in, that'll be exactly the same angle that I have coming out. In other words, in equals out. Incident is what the I is, and reflected is what the R stands for in this case, right? We're also going to use refracted in the next chapter. But so we have our incident ray, we have our reflected ray. We know for a plane mirror, a flat mirror, angle in equals angle out. This is also true for spherical mirrors, and we'll get to that in a second. So the law of reflection is for any mirror, okay? Angle in equals angle out. Now, there are nuances and some differences in the kinds of reflection you can have off of a surface. Let's see if I can remember the names for these. This is specular and diffuse. So here on the left is a specular reflection. Do you notice how the reflection comes in and there's a nice strong reflection coming off of that surface? Whereas over here we are getting reflection, but it's diffuse reflection. The beam comes in but then kind of heads out in all directions. This comes down to surface roughness, right? If the surface is really rough like it is here on the right, the law of reflection will hold. Angle in equals angle out. The problem is that the surface, the normal to the surface, is not consistent here, right? Because of the roughness, you'll have parts, right, that are pointing all in different directions. Well, what does this cause? Anybody that's ever driven around at night in the rain understands that all of the lines on the road disappear. You ever notice that? Yeah. Right? The reason the lines disappear isn't because the rain has washed the paint off. It's because there is a layer, right, of water on the surface that's giving you a very specular deflection. In other words, it's coming at you very intensely. In fact, it might even be horizontally polarized. Don't wear your sunglasses at night, okay? But it causes the features of the road to go away. Whereas this more diffuse reflection that you get, say, from a dry surface, okay, we can actually see some of the lines there, right? We can see some of the cracks in the road. So the nature of the reflection can be important depending on your application. Reflections from nice shiny mirrors are like purely specular, right? They're not diffuse at all.
Have you seen that ad for the sunglasses that you can wear at night? It's like, oh, it won't dim anything.
Okay, no, I haven't seen, but I don't watch ads, so. I firmly believe in ad blockers and sticking it to anybody that's trying to get me to buy something.
I guess I was just asking, how would that work? Like,
I have no idea.
oh,
It's probably a lie, just on the surface. You put anything in front of your eyeballs, you've automatically shut out some of the light. Now, if you wear glasses, they work really hard to not have that happen, right? Your doctor may have charged you for anti-reflective coatings and all that kind of stuff on your glasses, which are all actually really good coatings to have. Well, we're going to get to that when we get to thin films. But the idea of like having sunglasses that don't do anything, it's just called glasses, and I'm just, why put a piece of plastic in the front of your face if it's not doing anything for you? So, good question, though. All right. I want to use the flat plane mirror to introduce to you some vocabulary and some ideas that we use when we talk about optical systems, okay? I've already introduced one thing to you, which is the normal to the surface, right? Everything is measured not from the surface itself, but from an imaginary line that comes off directly from the surface, okay? The other thing about optics is that we're looking at images, okay, that are being formed in our optics. So whether this is a mirror or a lens, right, something is being caused to happen. So like I look in this, hey handsome, right? I look in this mirror and I see you and I see me, right? But there's an image, right, that I'm looking at. So just as an example, let's say this is your bathroom mirror, right? Like in my house, the bathroom that I use is on the second floor, right? And so if I'm standing on this side and I'm looking in the mirror, right, and I see myself, where do I see myself? Like where do I see you? Where do I see me? Like where is it?
the bathroom?
It's back here it's in the bathroom. Very good. It's back here somewhere, isn't it? Like if I'm standing 1 meter in front, real me is standing 1 meter in front, then image me, I see 1 meter back here, right? This is called a virtual image. Why is it a virtual image? Because I don't exist back here, right? Like the real me standing right here, okay, the real light comes off of me, hits the mirror, and bounces off and is collected by my eyeballs. Okay? But what do my eyeballs do? Or like what does my brain assume? Our brains evolved to understand that light travels in straight lines. Like most of the time when we're looking at light, if I see light coming off of you, coming to my eyeball, it didn't take like a circuitous path throughout the sky or the room. It didn't go to Pluto and then come back to me, right? It came directly, shortest distance, right, from the light coming on, and then it bounced off you, came into my eyeballs, right? And so my brain, as it tries to interpret what's going on in my visual field, is going, oh, well, light came from you, it came directly from you, right? So the light's coming into my eyeball, hits my retina, sends electrical signals to my brain. My brain has to integrate all that information, and it forms this idea, right, that the light must have come straight, and so if we follow that line back, we'll see the thing that we're looking at. When you put a reflective surface in the way, though, our brains start to have trouble. And the trouble is illustrated in this picture, right? So if you put an object, right, and you see it in a mirror, the light has to come from the object, bounce off the surface of the mirror, obeying the law of reflection, and then go into our eyeball. The problem is, what is our eyeball brain going to assume? Straight line, right? And so what our brain does is it sees these real rays coming into our eyeballs, and it traces those real rays straight backwards, creating an image in a place where it cannot possibly be. It's virtual because if I'm standing here and I look in the mirror, there is no thing back here, right? There's just no, in my house, it would be a 2-story drop to the backyard, right? Like but we see, this is true VR. This is the virtual reality, right? Looking in the mirror, okay? Is it the black mirror? Okay. So, all right. So, if what we see in a plane mirror is a virtual image, and the only location that a virtual image can form is where? In our brains. Virtual images form in your brain, okay? Because your brain is trying to make sense of what the light is doing, okay? The opposite of a virtual image is a real image. And I'll demonstrate real images when we get to lenses, because mirrors don't make them. Well, some mirrors do. We'll get to that in a second. This right here, the screen, the light that is hitting this projector screen is a real image. We are creating an image on the screen after it passes through several lenses, and I know this is a real image because I can interfere with it. Do you see that? Like I can get in the way of this image and cast shadows and all that kind of stuff, right? And our brains look at this real image that's formed on this screen, and then our brains interpret what's going on, right? This is a real image, whereas the image in a mirror is a virtual one, right? If I try to interfere with what you are seeing back here, does it change anything? No matter what I do back here changes nothing. Because where is this image forming? In your head. It's all in your head. This one forms in your brain. That one forms on the screen, right? And I can get in the way of it. So real image, virtual image, we'll give you some more tools on how to figure out what the difference is. Okay, so what have we talked about? We've talked about the normal. We talked about law of reflection. We've talked about real versus virtual images. I want to talk about the nature of reflections very quickly, okay? Because there's a problem, right? When you're looking into a mirror, right, and you got the mirror, right, and you raise your right hand, what does your virtual reality doppelganger do? It's the left hand, isn't it? You trying to tell me I part my hair on the other side? Yes, that's what I'm trying to say. Okay, so the question is, which way do mirrors flip images? This is called image orientation. Okay, so there's an inverse somewhere. Okay, and there are 3 choices for the direction of inversion, if you will. Okay, or the flip that a mirror will do, or a lens in that matter. Okay, images can either be flipped left to right, up or down, or in and out. We call that a front to back in optics. Okay. My question, and basically those follow the XYZ axes, right? So there can be a left to right or horizontal, up to down, which would be vertical, and then front to back, which would be in and out. Okay? So the question I have for you right now is, which way do plane or flat mirrors invert the image? Front to back, up or down, or left to right? Left to right? Yeah. Well, that's your guess, your hypothesis. Let's see if we can't prove it true. How do we prove things true in physics? We do an experiment, right? Okay, so let's do an experiment. What would a up or down image flip look like? It would literally invert the image and make it upside down. So instead of me seeing me in this mirror right side up, I would see me standing on my head. And is that what happened? No, you don't stand. If you're standing on your head in the mirror, then you're standing on your head in real life. I hate to break it to you. Okay? So this is very definitely not a up-down inversion, right? So that leaves two more. It can either be left, right, or front, back. You said left to right. How do we prove it? The hint is not with your hands. Piece of paper with writing on it?
Yeah.
Oh, but it's mirrored, isn't it, Mr. Balogh? Right? I hold it up and actually, it's not. Here's my pen, okay? Which way is my pen pointing? My real pen? It's pointing to the right, isn't it? Okay. In order for a left to right reflection to happen in the mirror, if I put the pen in the mirror, which way would the tip be pointing? It would have to point left, the opposite direction. Okay, are you ready? Which way is the image of the pen pointing in the mirror? Same direction. It is not a left to right flip. You've been led astray your entire life, and I'm fixing you. Right? Okay? That's a piece of knowledge that up to this moment, I bet you guys would swear was correct. Of course, right? It's a left to right flip. Duh, everybody knows that. Well, guess what? Everybody's wrong. Okay? This is not a left to right flip. It can't be. The proof is right here, right? The pen would have to be the other way. So what does that leave? If it's not up or down, and it's not left to right, then the only choice that remains is front to back. And when you imagine a front to back inversion, I'm guessing in your brain you get the idea is, where if I look in the mirror, I would see the back of my head. That's not a front to back inversion, okay? That's holding two mirrors, or your cell phone and your iPad or something, whatever you do nowadays, right? Okay? To see the back of your head. I will now demonstrate that this is a front to back inversion. This can be a little bit hard to tell because my pen is small, my mirror is small, so I might use people in the front row here to help me here. But if I take the tip of the pen and I point it towards the mirror, okay? What part of the pen are you looking at, the real pen?
I'm looking at the back.
You're looking at the back end. You see the back end of the pen. But what do you see in the mirror? The tip. You can try this at home. Maybe do it in the bathroom where nobody can see you so they don't think you're too weird. Okay? Take a pen, hold it up, see that it doesn't flip left or right, and then hold it, right? You're looking at the back end. But in the mirror, you don't see the back end. What do you see? The front end in the mirror. That is a front to back inversion. So why is it that so many people wander around with the wrong information in their brain about what mirrors do? Answer, Congress. No.
Oh, is it because of how we see each other?
What?
Is it because how we see each other?
Not each other.
Like
Yourself?
It's how you see yourself. What did my doppelganger just do? Raised his left hand? Your right hand's mirror or front to back image is your left hand. Human beings have a line of symmetry, exterior line of symmetry. Our organs are not symmetrical. Some are, like the kidneys, right? But we tend to only have one heart or whatever, right? Okay. So externally, we have a line of symmetry that kind of goes down the middle of our bodies, okay? We are not perfectly symmetrical left to right. one of your eyes is taller than the other, one of your nostrils is bigger than the other, one of your arms is whatever, right? Okay. As human beings, we actually tend to freak out. It's called the uncanny valley. If we see like a digital representation of a human being and it's too like symmetrical, our brains go, not real, run away, panic, panic, panic. Okay. It's how we can tell like CGI from not and all that kind of stuff. The inherent flaws in our symmetry is what cues us into the fact that a person is real. Okay? But getting out of the psychology of it a little bit, the mirror symmetry across our bodies, okay, is not a left to right symmetry. It's a front to back symmetry. Your right hand and your left hand are front to back inversions of each other, which leads to the confusion, right? When your doppelganger, when you raise your right hand, it's a front to back inversion. So what are you seeing? You're seeing your left, right? Because the thumb, right? And all that kind of stuff. So that's where the confusion comes from. And that's why like mirror writing isn't the left to right. You don't see the word written backwards. You see the letters flipped front to back. If you see an ambulance, don't chase one down while its sirens are going, but just find an ambulance. At the front, on the front of the ambulance, on its hood, it will have the word ambulance written, okay? Ambulance, but it will, some of the letters will be flipped around because they want the person that's looking in their rearview mirror to see the word ambulance, right? The A is still in the A position. The M is still in the M position. It's not like the A comes over to this side and goes backwards, right? But some of the letters. Now an A and an M, you can invert them front to back and nothing changes, right? But L has a problem, right? Okay, C has a problem. E has a problem, right? You got to get the... So it's front to back. It's not left to right. Okay, so that was plane mirrors. Let's move into spherical mirrors. And I brought some examples, okay, of spherical mirrors. Okay, this is one of them, and you've probably seen this one in a hospital or in a store or something, usually up on a corner. Okay, what does this do for you? You can kind of see around the corner, right? The security cameras will be pointed into these to increase what we call the field of view. Okay, so unlike a plane mirror, like if I hold the plane mirror up in the corner, can you see very much of the room? Right? You can see kind of directly what the mirror sees, right? But this spherical mirror warps our perceptions, right? Okay. And allows us to see more of the room. The field of view of the mirror, the amount of the room that we can see has been increased. Okay? Now we can start talking about magnification. In a plane mirror, there's no magnification. Things don't look bigger, things don't look smaller, they look their normal size. But what does this room look like in this mirror? Does it look enlarged or reduced? Reduced. It's smaller, right? This image, which is what kind of image? Real or virtual? Virtual. How do you know it's virtual? It's got to be in your head because there's no small room on the other, right? Nothing small back here, okay? This image, right, being a virtual image, is reduced because it's smaller. Things in the mirror appear smaller than they actually are. And we say that it's upright. So your choices are real or virtual, enlarged or reduced. There's actually a third choice in there, which is no change, right? And then upright or inverted. What do you see in this one? Whoa. This is an upside down one. Okay? So, Is it upright or inverted? This one's inverted, right? You're seeing things upside down? Okay. Enlarged or reduced? Do things look smaller or bigger in the mirror than they actually are? A little bit smaller, right? So slightly reduced. Here's the tricky one. Real or virtual? This one's real. Real and virtual is hard when you're looking at it. We'll draw pictures that will guarantee that we understand what's going on. Okay, but we're going to get to that in a second. But I wanted you to see this is a real image that's forming. And this image is actually forming like out in the front of the mirror. Okay, and that's what you're seeing. Whereas this mirror over here can only make virtual images no matter what.
Is it because of the shape of our eyeball?
Nope.
It's the angle of the...
It's because the brains are weird. Okay? I am now going to create a virtual image with this mirror. This is difficult to do for everybody in the room to see. I'll try at the end to make it so everybody can see. But I am going to pick on some people here in the room. And what I'm going to do is I'm going to walk up and I'm just going to have them look in the mirror. And, well, okay, what happened?
The light got super bright.
Oh, the light got super bright. Sorry, we'll do it this way.
Oh, it's the thing with the...
The thing with the thing. Yeah, okay. What did you see?
Makes my face super big.
Made your face super big? Yeah? Yeah? The reaction that most people have to this is like, okay? And if in lab, I'll try to get these out so you guys can experience it yourself. I can kind of cheat it a little bit. Can you guys see that? Is it working? Can you see it now? Does my face look kind of big? No? Yeah, can you see it?
Oh, there it is. Oh, there it is.
Okay, okay. Ah! It was like Halloween, right? Okay. But did you see how my face got really big?
Yeah.
Okay. That's kind of what the people were seeing, right, in the mirror. This image is virtual. Okay. It's upright. Did you notice my head wasn't upside down? Okay. And it's enlarged because it's much bigger than it needs to be. Not to be too sexist about it. I just want, it is California and all those things. And so you can use whatever you want to use. But let's just say, ladies, what is this? Where have you used this kind of mirror before? Yeah, this is a compact mirror, isn't it? Or a makeup mirror. Gentlemen, where have you used this before? Shaving mirror. Most guys don't even know what a shaving mirror is anymore. But you can get one. It is a makeup mirror. Okay? It just allows a very big, I can pop some zits, right? Like you can really get in and see up close, okay, in the mirror, right? Things that you may not be able to see in the bathroom mirror, okay? So there's advantages and disadvantages to all the different kinds of images that can form in these things. And so let's start nailing down like some math and some predictability and like, how do I know if it's real or virtual? This is all kind of weird. So when we say a spherical mirror, we're talking about the cross section of the curve. You can actually have plane or flat mirrors. You can have spherical mirrors where this surface curvature is like we made a sphere and cut a portion of that sphere out. That's not how we make them, okay? You don't make a big spherical mirror and then cut portions out of it. You don't do that, right? But geometrically, okay, this is a spherical mirror because it curves consistently throughout. You can have parabolic mirrors, which have a parabolic cross-section to them. You can have hyperbolic mirrors, right? Not hyperbolic, there's parabolas, hyperbolas. Yeah, hyperbolic mirror, okay? Where the curvature is such. As a matter of fact, in your car's headlights, there is the headlamp, and behind it, there's a mirror that is a parabola, okay? Parabolic mirrors are really good for taking light and like sending it, okay, in a certain direction. So, but we will only do plane and spherical stuff in here. Our lenses will be spherical. Our mirrors will be, right? We're not going to do parabolas or hyperbolas. So what's going on here? In the language of optics, okay, the conventions of being able to talk about what's going on, you have what we call the optical axis. And this is, by the way, this is called a ray traced diagram or a ray tracing diagram. Movie buffs, where have you heard, or video game players, where have you heard the term ray tracing before? Expensive graphic card, okay? The very first movie to use ray trace technology was Toy Story. Okay? Toy Story, Pixar engineers pioneered the computer graphics where instead of them like animating frame by frame, they programmed the computer to trace light rays throughout the scene. They had emitters, things that were causing light, and then they had material properties, like all the different plastics of the toys and the fabrics and things like that. And they had the computer render frame by frame what the camera, virtual camera was seeing as the actual physical properties of those light rays came from the sources, interacted with everything in the scene, and then came to the virtual camera. What I'm about to teach you, the principles of ray tracing, is exactly what they were using and still use today in video games and movies. A ray traced image is literally calculate the physics of the actual rays. What does the light ray do when it hits something, right? And then follow it back to its source. All right, so we have this optical axis, okay? And even though a lot of books don't talk about it, it's still true. The point at which the optical axis intersects the mirror is called the vertex, okay? I don't think you'll run into that in your book, but you'll run into it on the internet and stuff like that. So here's the optical axis. The vertex is this point here, okay? There is what we call the radius of curvature. So back to our sphere, right? If we knew the radius of this sphere, right? Then the radius of curvature at the mirror would be where like the center of the sphere would be. Okay? And so we label the point where the center of the sphere would be as the as C, right? The center of the sphere. Okay? Point of, I can't remember what it's called. Anyway, radius of curvature, vertex, principal optical axis. A light ray comes in, interacts with the material, with the mirror. Remember, the law of reflection says that the angle in has to be equal to the angle out. And that angle is normal to the surface. And because it's a curved mirror, those normals are changing their direction consistently. And that ray will come and do something, okay? Notice we have two different kinds of mirrors here. I had two different mirrors in my hands, right? The concave mirror, the way I kind of remember that is that the bear has to walk into the cave, right? Do you see how it's like opening up? Oh, yeah. Right? Okay. So the person has to walk into the cave opening, right? And then convex is not walking into the cave, right? Convex is it's bent outwards, okay? Now, they haven't really labeled it really well on here, so I'm going to do it. The front side of any optic, any mirror, any lens is the side that the object is on. There's always something that's causing a light ray to happen, okay? The front side is always the side of the object. So if we drew a ray trace diagram and we had this and our object was standing right here, this would now be the front side. In optics, we don't really say left or right, up or down. It's either we're in the front or the back of the optic. Okay? For a mirror, the front side is also the shiny side. Front side, objects would be over. I mean, if I put my hand back here, that doesn't help, right? Can you see my hand? No, because what's the front side of the mirror? This one, the shiny side, right? For lenses, it gets a little bit more confusing because there isn't a shiny side. So sticking with this idea that the front side is the side with the object on it, okay, the thing that's causing the image to happen, it's a little bit easier. So again, this would be the front side. This would be the back side, okay? And you can see here the concave mirror and the convex mirror are kind of doing different things with the reflected ray, okay? Again, following the law of reflection. Every spherical mirror has what we call a focal point. The point at which light, traveling parallel to the optical axis, will bounce off the mirror and then go through the focal point. The focal point, or the focal length of the mirror, is always the radius of curvature divided by 2. For a spherical mirror, that's always what it is. Okay? Doesn't matter what?
So the radius divided by 2.
Yeah, it's the radius of curvature divided by 2.
Okay.
Always.
Does the curvature matter?
Well, yeah, because that determines the radius of curvature.
Okay.
Does anybody still get their TV this way? Right? What is this? Satellite. People are getting their internet like this now. Okay? So it's a satellite dish. What is it doing? It's bouncing the signal. It's gathering it from a satellite that's way far away. So the radio waves that are coming from the satellite, radio waves, by the way, are electromagnetic radiation. They're light waves. They come down, and by the time they reach Earth, they are basically parallel. They're moving parallel to the optical axis of this dish, of this spherical dish collector. This one happens to reflect visible light. This one reflects radio waves. Okay? Where are they putting the sensor, the receiver, the part that receives all of the radio signals? Where do you think they put it? At the focal point, right? Because all of those parallel rays are coming from the satellite way far away, and they get focused down into the receivers so that the receivers have a lot of signal to work with. Okay? So it doesn't have to be visible light. Optics work in every part of the electromagnetic spectrum. It gets a little bit trickier when you're like in the X-ray portion of the spectrum, right? Because what do X-rays usually want to do? They want to go through things, right? X-rays travel through the body until they hit like minerals in our bones, and then they bounce, right? But otherwise they just go through. So my graduate work specialized in making X-ray mirrors. Okay? They weren't optical mirrors like with our eyes. You couldn't like see the reflection. But what they did is they were really good at reflecting X-rays, which again is a trick. It's a good one. By the way, why does this one have 2 receivers on it? No? No? You guys are not old enough. One of those is the SD signal, and the other one is the HD signal. Standard definition. Okay? In the days before 1080p or 4K, there was 480i interlaced signal. And that's standard definition. What this is, this dish is actually not quite spherical. It's receiving both the HD and SD radio waves, and they have slightly altered the curvature of the dish to make sure the frequency that's the HD goes into one receiver, and the frequency that's the SD goes into the other receiver. We don't have SD signals anymore. Everything is HD now, unless you're on Twitch and you put the resolution way down. All right. I guess YouTube has that resolution slider too, but people don't mess with it as much as they do on Twitch. Okay. The good news is you guys don't have to worry about drawing ray diagrams, ray trace diagrams. Oh, I didn't log in. Can I just, I better do it this way. 1 second, didn't have the computer all set and ready to go like I should have. Yes, authenticator, you are allowed to Log in. Come on. Does anybody else besides me just absolutely hate the Microsoft Authenticator? Like, I love two-factor authentication. I do. Like, I think it's a good idea. But like, the way Microsoft's implemented it, somebody needs to be shot. Like, seriously. Like it's just, it's not good. All right. I should not advocate violence, but there you go. Choose content. Yeah. Okay, let's go to here. All right. The reason we don't have to really draw ray diagrams anymore. Some teachers still believe this is important, but I don't. Yeah, and I'm an optical physicist, right? If you come down here to Unit 3 Optics, there will be a link to optics simulation, okay?
You see like a random website.
Darn it. That was totally my fault because I hit computer and what I needed was USB-C. Sorry, okay? If you go to modules, right, and you scroll down to Unit 3 Optics, which is where we are, right, 24, 25, optics simulation, PhET, geometric optics, that's physics education technology, I think is what that stands for. And you click on that link, okay, you'll end up at this site. It's totally free, okay? You come in here, we're going to do mirror. This will work for lenses, but we're going to do mirror, okay? This simulation will do all of the ray tracing for you. Let me help you with the setup here a little bit, though. Instead of a pencil, I would suggest an arrow, but if you want to do a penguin, you can do a penguin. Okay, do an arrow. Arrows are like the easiest thing to understand what's going on. Also, the rays do principal rays, okay? There's different ways to do all of these rays, okay? But principal rays are the standard ray tracing rays. There are other kinds for sort of understanding what's going on, but the principal ones are the ones that we're going to focus on. You can mess around with all the other things, okay? But the cool thing here, right, is that you can drag the object around and then you can see the image that is forming, right? We'll come back to that, okay? In optical diagrams, there are three principal rays that we draw, and they follow certain rules, like the rule of a ray comes parallel to the optical axis, bounces off, and passes through the focal point. A second ray passes through the focal point, strikes the mirror, and bounces parallel to the optical axis. This is just following the rules of the law of reflection. And then the one that passes through the center of curvature bounces off and comes straight back through the center of curvature. Okay? When you put those three together, okay, what you get, so we have the first ray coming through, we have the second ray through the focal point going like that, and we have the third ray going through the center of curvature. Where those three rays meet, like since we drew them leaving the tip of the arrow, that has to be where the tip of the arrow is. Okay? If we move the object inside, things change. Okay? And if we have a convex mirror, again, we have different things that are going on. I'm going to go through all of these. Okay? But before I get there, I want to hand something out. Okay? I'm going to give several of these, and we'll pass them down this direction. Okay? So back in the old days, they handed these things out in our classes all the time. This is called paper. Okay? And the reason I'm giving you this on a piece of paper is because I want to underscore the absolute criticality of these conventions. Okay? I've given you all of them. Do we have the right number over here? Yeah. I've given you all of the conventions on this sheet. So both mirrors and lenses. But we really just need to focus on mirrors now. Okay? But you can crumple this sheet up. You can throw it away. You can put it on your bathroom mirror. You can take a PDF of it. Well, I don't care what you do with it. But we will refer to this so much. I wanted to underscore its importance by giving an actual physical version to you. Okay? And we'll get more into how that works maybe on Monday. Monday's lab is lecture. We're not ready. You're not prepared. for the lab that we're going to do in optics, okay? Because our optics lab has more to do. It's a lenses lab. It's not a mirrors lab, okay? But what we're going to do in lab on Monday is more lecture. I'm like going to continue, and we're going to lay down how to use these conventions for mirrors. And then we're going to translate all of what we've talked about today and what we learned about mirrors. We're going to superimpose that onto lenses, okay? And then start talking about how to fix eyeballs and all that kind of stuff. Back to this simulation though, okay? This is kind of one to have in your back pocket. Obviously, you can't use it on the exam, but like as you're trying to visualize what's going on in the problems, you can use this simulation. So one thing I'm going to do is I'm going to lock the height so I can just move this back and forth. But do you notice, so here's my object, right? This blue arrow that's sticking up right here. And I can move it like way away. I can bring it like up close. But do you notice what happened? Like what kind of image is being formed here? So again, we can describe an image as real or virtual, upright or inverted, magnified or reduced. What about magnification? Is this image, the place where the rays are coming back together, is it magnified or reduced? It's reduced. Do you see how it's smaller than the object? So it's reduced, okay? Is this image upright or inverted? This is an inversion. Do you see that? The arrow was pointing up, and now it's pointing down. If you're using the penguin is upside down, right? Okay, so but arrow is the standard, okay? Real or virtual, and how do you tell? This is a real image. It's a real image because real actual light rays converged at a point. Let me now make you a virtual image by not changing the mirror at all. I moved the object inside the focal length of this mirror. Okay? In doing so, our eyeballs, which are over here, like on the front side of the mirror, we got the object and we have like our eyeballs, right? So our eyeballs are seeing these three rays, which are diverging from each other, right? So they go to the left, they're just spreading out, they're never going to come back together again, right? And so what does our brain do? It follows those rays back to make a virtual image. Dotted lines indicate virtual rays. And in this case, virtual rays are converging in order to make a virtual image, right? Virtual image, upright or inverted? Upright. Magnified or reduced? Magnified, okay? So this is the makeup mirror. This is the shaving mirror, right? Okay? Putting your face inside the focal length of the mirror. If we're outside the focal length, what sort of image do we get? Real, inverted, in this case magnified, right? But if I slide it over here, it becomes reduced, doesn't it? And we're going to actually calculate all of this on Monday. We'll teach you how to do all the calculations, okay? You can flip this to the convex mirror. Now here, a convex mirror is always making what kind of image? It's always virtual. There's like no choice there, okay? So convex mirrors, guaranteed always virtual images. It's the concave mirrors, right, that can kind of bonk, right? See, we went to a virtual image, or we have a real one. So this and other like simulations like it, ray tracing simulations, can help us visualize what's going on, right? You won't be able to like exactly input the numbers and all that kind of stuff, but you can like, if you know the focal length of your thing is 30 centimeters and the object is at 40, well, then it's this kind of picture, right? There's the focal length. My object is outside the focal length, right? It was 40 centimeters. My focal length's 30. I'm going to get some kind of inverted, real image. Whether it's magnified or reduced, well, that's going to come out in the math, right? But if I knew that my focal length was 30 centimeters and my object distance was 10. Well, that means my object's inside the focal length. And based on my ray trace simulation here, what kind of image are we going to get? Virtual, magnified, upright. Not all virtual images are upright. If, and only if, there is a single optic, in other words, a single mirror or a single lens, then if the image you see is upright, 100% chance it's virtual. But that only works, I can't be careful enough here. That only works if there's a single mirror or a single lens. As soon as you introduce multiple optics in a system, all bets are off for that rule. Okay? So I'd much rather you look at a ray tracing diagram to determine whether it's real or virtual. But there is a shortcut as long as there's only one lens or one mirror, right? If the image you are seeing is upright, it's a virtual image. Okay? All right. We will get into the sign conventions, how to calculate all of this stuff. We'll get into that on Monday. How are your brains doing with this? Like difficulty-wise compared to electric and magnetic fields? It's a lot more chill, isn't it? I threw a lot of words and definitions at you today, right? But it's not like hard to understand, right? Welcome to optics.